Draw the shear and moment diagrams for the beam. Indicate values at the supports and at the points where a change in load occurs. To begin, let's convert our uniform distributed loads into point loads. So for the first part or first half, we're gonna have half times 2 times 6, which is 6, and so is our other half. Each load is 2 meters away from the center. Now we can determine our external loads. Our AX is going to be 0, while AY and BY are unknown. We're going to take a moment about the point B. In order to find a solution for AY, so we can have X counterclockwise 4 meters or 4 feet away, and then we have counterclockwise 6k pounds, and then 8 meters away. Finally, we have clockwise AY 12 feet away, all equals to 0. Solving for AY, we get our solution as 6. And looking at the symmetry of this beam, we know that BY is going to be the other 6 remaining out of the 12 that is being exerted on this beam. Now we have our moments and our reactions. Now we can start drawing our moment diagram. So we're gonna begin at 6k, and then all the way till 6 feet, we're gonna come down by 6k, which will bring us to 0. And since we know that our load is negative increasing, this means our negative decreasing. Or another way to look at it is that as we're going further and further away from point A, the shear is increasing, and this means our curve is going to be concaving down. Then we have the other half that will bring our shear curve all the way to -6. And in this case, it's negative, but its higher value or higher amount is on the beginning side, and it also means that our negative is increasing. Therefore, our curve is going to concave upwards. And then from BY, we're going to go 6k up, which will bring us back to 0 and confirms that our calculation were correct. Now for our moment diagram, we have a second order curve for the whole of the shear diagram. And we know that wherever shear is 0, you're going to have a flat moment curve or curve that would tell us either the maximum or minimum of the moment. In this case, our moment is going to begin at 0. And now we just have to find the area under the shear curve from 0 to 6 feet. And our area under the first shear curve is positive 24. And we get it by using the semi-parabola area formula, which is 6 by 6. And then finally, we're going to use the same formula, but it is on the negative side, so our curve is going to go downwards. Curve is going to draw the moment diagrams for the frame. Assume the frame is pin connected at B. To begin, let's draw the free body diagram for BC. And because B is pin connected, there's only going to be vertical and horizontal reactions on it. And Bx in this case is going to be 0 because there isn't any other horizontal force acting on it. Cy is unknown, and our point load from the uniform distributed load is 30 kg, and it's 1 feet away from C. Now we can take a moment about the point C to find our solution for By. So we're going to have 30 kg times 1 counterclockwise and clockwise By, and it's 6 feet away, all equals to 0. So for By we get our solution as 5 kg. And then for Cy we're going to have 30 take away 5, which is 25. So Cy is 25 kg. Now we can draw the free body diagram for the remaining portion of this beam, which is AB, and it's 10 feet away. By is 5 kg. Bx is 0, so we're not even going to write it. And then 8 kg acting horizontally, and then Ax, which is going to be just 8, opposite of 8 kg, because there is no other way for this beam to resist the external action force of 8 kg. And then our Ay is simply going to be the opposite of whatever our By is, and it's 5 kg in this case. And then we're going to have a moment about this point at A. To find our moment, we just simply have to sum the forces about the point A. So we're going to have unknown moment A, and then and this is counterclockwise, so positive, and then we have clockwise 8 kg, and it's 5 feet away, all equals to 0. Solving for moment A, we get our solution as 40k feet. Now we can start drawing our moment and shear diagram, because we can straight go to moment diagram, but I would recommend drawing the shear moment or shear diagram, because it gives you a little bit of context of what's happening. Okay, so for our member AB, so we have 8k shear, and then a go in a straight line, which is our zero order line or slope, and then we have 8k. Acting on this beam midway through, and then it flat lines all the way to the 10-meter mark or 10 feet mark. Now to draw our moment diagram, we simply need to find our area for this rectangle here, which is positive. So we're gonna have and another thing is, before we even look at the area, we have to remember that we have initial moment A counterclockwise. So counterclockwise is always negative on the graphs or diagrams. And then now we have to calculate our area for the shear here, which is going to be 8 times 5, which is 40, positive 40. So our moment will flat lines to 0 and all the way to 10 feet after 5 feet. And this slope is first order slope. Now we could have done this problem a little bit different as well. So if we didn't want it to draw the shear diagram, and it would go something like this. So we know that our shear equation is going to be just 8 for the section 0 to 5 feet. And then our moment is simply going to be 8x plus c. And we know already that our moment is 40 when x is 0, therefore our c is 40. And in this and we write in this equation, we get equation something like this. Now we can continue with our shear diagram for the other half or the remaining half of this beam. And for this section, we begin with positive 5k shear, and then we have uniform distributed load goes all the way to the end of the beam, but in between, at after 6 feet, we have our CY, which is going to change things up a little bit. Okay, so to determine, first of all, our effect of the uniform distributed load, so we just have to do area of rectangle, which is 3 times 6, which is going to be 18. So 5 take away 18 is negative 13. So at 5 feet mark, We're going to have negative 13 as our shear. And then we can have CY, which is positive 25, so negative 13 plus 25 will give us positive shear of 12. And then we're going to do the remaining area of rectangle for the remaining of the uniform distributed load, which is simply 3 times 4, which is 12, and that will get us back to 0. Okay, so that was that. But now we need to determine our point of intersection. And at this intersection, we can have our max or minimum moment. Okay, so our load equation is going to be simply cross section and 0 to 6 feet. It's going to be -3, and then our shear is going to be the integral of load equation, which is -3x plus c. And we know that when x is 0, our shear is 5, therefore c is positive 5. So now we can determine when our shear is 0, what is our value of dx. And this comes up to be 1.67 feet. Now we can start drawing our moment diagram. For moment, we know we begin with positive, but we don't have any moment at 0. So we just need to find the area under our first intersection before the 1.67 mark. So it's going to be 0.5 times 1.67 times 5. This gives us our first mark, which is the positive 4.17. Then the remaining portion of this triangle, so this is going to be 6 take away 1.67 times -13 times 0.5, and this gives us -28.45. Which is basically rounding it off, -24. And its curve is going to be concave down, something like this. We'll have to find our point of intersection, which we'll do later. But now, let's find the area under this rectangle. And this is going to be 0.5 times 12 times 6, pardon me, 4. And this comes up to be positive 24. And this curve is going to look something like this, concaving downwards. Second order. All these are second order, by the way. Okay, now let's find the point of intersection. To do that, we just have to take the integral of our shear equation. So it's going to be moment x equals to negative 1.5 squared plus 5x plus 3. And c we know is going to be 0 because we be at 0. Now we can find our value for the x where the intersection occurs. So it's going to be negative 1.5x squared plus 5x. Solving for x, we get our solution as 0 and 10 over 3, which is 3.3. There we